Welcome into Calc 3. Today we talk about partial derivatives, right? So in Calc 1 we were doing normal derivatives, right? Now we're going to do partial derivatives because we're dealing with multivariable functions, right? So let's get into the notation side, right? How do we even notate this? So let's say I have some function f of x, y, and I want to take the partial derivative with respect to x of f of x comma y. And I'll pause here for a second. So how do we read this? I'm taking the partial derivative of f of x, y with respect to x, right? Another way of notating this, let's grab a different color, is maybe we see f sub x of x comma y, right? So this is another way of notating it. Okay, so what does this mean, right? As far as a calculation, and again, we're going to do an example here shortly, right? So what does this mean? Well, the intuition, right, is that we're taking the instantaneous rate of change in the x direction, holding everything else constant. So in this case, we're going to hold the y constant, or think of the y as a constant. So what does that mean? We're going to treat x as a variable, which means we're going to treat y as a constant. So again, when we get to an example, this will make more sense. X is the variable. We're looking for the instantaneous rate of change or the slope in the x direction, holding everything else constant, meaning we're going to hold the y constant. And same thing here for partial with respect to y, right? So this looks similar. We have the partial with respect to y of f of xy. And what does this equal, right? Well, this is equal to the other notation. We'll just say f sub y of x comma y. So either of these notations are fine. Right, and what does this mean? Well, this means we're going to treat y as the variable. And that means if we're treating y as the variable and we're holding everything else constant, that means x is being treated as a constant. And again, this is going to feel a little strange at first because, right, normally we treat variables as variables and we treat constants as constants. So now we're going to be treating a variable as a constant, right? So again, instantaneous rate of change in the x direction, holding everything else constant. Instantaneous rate of change in the y direction, holding everything else constant. We need this because, as you can see from our three-dimensional graph over here, right, we have slopes in different directions. Since we're in 3 dimensions now, we have slopes in the x direction and slopes in the y direction. Okay, let's do our example over here. So let's say I give you some function, f of x comma y is equal to x squared plus y squared plus 2xy. And my very first thing I'm going to do, let's just go ahead and do the partial derivative with respect to x. Okay, so let's work through this and read as we go. So derivative with respect to x of x squared, we're treating x as a variable, so this is normal, 2x. Okay, first kind of tricky part. Derivative of y squared with respect to x, and we're treating y as a constant. Well, y squared then would be a constant by itself. Derivative of a constant, 0. Right, so again, it'll take a little bit of getting used to. And derivative of 2xy with respect to x. Right, so we're taking the derivative of x here, which is 1, and 2y is just a constant hanging out. So we end up with 2y. And we can simplify, right? No need to write this 0. 2x plus 2y. So what is the interpretation here? You give me some xy point, right? I can plug it in and find the instantaneous rate of change in the x direction, holding everything else constant. That's why we treat the y as a constant. Okay, let's do the other one, f sub y. Maybe pause the video if you're comfortable enough and do it yourself. So in this case, now I roll up to my x squared and I go, okay, I'm treating x as a constant. because I'm taking the derivative with respect to y, derivative of a constant is going to be 0. Derivative of y squared with respect to y, 2y. And derivative of 2xy with respect to y. So we're treating y as the variable, derivative of y with respect to y is 1. 2x is a constant hanging out in the front. And of course, we don't want to leave our answer like this. Let's simplify it. We don't need the 0. We have 2, and I'll just rewrite it the same. So in this case, and I should point out this is not always the case, these partial derivatives are the same. We're going to see in examples after this that is not always true. Actually, very rarely is it true. Right, but in this case it is. Again, the interpretation, you give me some xy point, I can give you the instantaneous rate of change in the y direction, holding everything else constant, or holding the x constant in our case. Right, so that is it for this video. Again, think of how this relates to our visual over here in 3 dimensions. That is it, and we will do some examples in the next part of the video. All right, welcome in. As you can see, we have these examples already written up for you. Feel free to pause the video, work through them at your own pace. I will go ahead and get started, starting from first column to the second column. Okay, so our very first one, we have f of xt is equal to t to the 8th. And we're just going to go down the line. First one we'll solve for will be f sub x of xy. And in this case, right, we're treating x as the variable, and we're treating, xt, sorry. Let's rewrite that. xt, we're treating x as the variable and t as the constant. So in this case, a constant just hangs out here in the front, right? Nothing for us to do. Derivative of cosine is going to be negative sine, so I'll put the negative out front, and we have sine of x. So again, as we're doing this, we're treating x as the variable, t as the constant, and now when we get to our next example, for f of t, not to be confused with y, f of t of xt, we're treating t as the variable, x as a constant, so derivative of t to the 8th, 8t to the 7th, cosine of x, the entire thing is just a constant that's hanging out at the end. Right, so pause the video if you want to go through that one. Feel free to work on number 2. I will jump into doing number 2. So this one here, similar idea as above. A little bit of a mini chain rule here. So we have f of xy is equal to e to the negative 6x sine of y. Now we will do f of x first, of xy. Meaning we're treating x as the variable. Sine of y here is just a constant. Right, so derivative of e to the negative 6x, we have a chain rule. Negative 6e to the negative 6x. Sine of y is just hanging out. Awesome. And our bottom one down here, f of y, x comma y. That means we're treating y as the variable, so sine of y. E to the negative 6x is just a constant that's hanging out in the front here. So nothing to do with it. Derivative of sine is going to be cosine of y. Awesome. All right, so these are kind of the basic 2 examples. Right, once we get over to these examples over here, we have a chain rule situation. Right, where we have an outside function of sine, right, and then we have p's and q's on the inside. So there's a chain rule for these. So let's do f of p of q. Now the derivative of the outside function here is sine has both of these, right? So just worry about the derivative of the outside. In this case, it's going to be cosine, right? The inside stays the same, and I've messed up my spacing a little bit, but it should be fine. Right, inside stays the same. Now derivative of the inside with respect to p, treating p as the variable. So we end up with 4p cubed q to the 6. Right, so again, the derivative of the inside is where we actually see the partial derivative of p, right? Derivative of p to the 4th, 4p cubed, q to the 6, constant that is just hanging out. And you'll see, you'll notice for f of q here, this follows a similar pattern, right? Where in this case, our outside function sine, right? The outside derivative is the same for both of these because it includes both p and q, right? So the derivative here is also going to be, the outside function will be cosine, leave the inside alone for right now. And the derivative of the inside, right, now with respect to q, is going to be 6. P to the 4th is a constant hanging out. And we have the rest of our power rule here, q to the 5th. Awesome. Right, so both of these, right, you'll see again, the derivative of the outside function applies to both p and q, so it doesn't matter which one you're doing, the derivative of the outside is the same. Once we do the derivative of the inside, we take it with respect to p and q. Now, same idea here. Now, for natural log, we do have our rule from Calculus 1 about the chain rule with natural log. So I'm going to assume we already know that. If we don't, I'm throwing it over here in the corner for you to reference. So let's go ahead and we will do f sub x of x comma y. And because we're a little short on space, I'm going to write my fractions a little bit funny. Right, so according to our rule for natural log, our function x cubed plus y to the 6 goes in our denominator. So x cubed plus y to the 6. That is a 6. I feel like I might have made it worse. And since we're taking the partial derivative with respect to x, we're taking the derivative of the inside with respect to x and putting it in our numerator. So in this case, 3x squared. Right, easy enough. We will mimic the same thing for f sub y. I have to get a little low here. F sub y with respect to, or f sub y of x of y. Same idea, our denominator, x cubed plus y to the 6. And now the derivative with respect to y is what's going to go in our denominator of our inside function, right? So derivative of x cubed with respect to y would be 0. That's why it goes away. And this is just 6y to the 5th. Right, so chain rule, think of level 1, level 2. We'll do one more part here, which will be like a level 3 video. But hopefully these examples helped. Again, what are we doing here is we're taking the derivative, right, we're doing what's called the first partial derivative, but the intuition is we're finding the instantaneous rate of change, right, in the respective directions, in the x and t directions, and the x and y directions, etc. Right? So if I give you some point to plug into one of these functions, you can tell me the rate of change in that particular direction. All right, we'll have some visuals over here to help. Again, natural log rule, the better we are with our calculus 1 derivatives, the easier these will become. So I will see you in the next part of the video. Welcome back. Let's go ahead now and jump into second partial derivatives. So we had first partial derivatives dealing with instantaneous rate of change, second partial derivatives dealing with concavity, right, in that particular direction. So let's say we have some arbitrary function, we'll say it's z is equal to f of xy, right? Awesome. And I want to take the second partial derivative. So what are all my options here? We'll go through them piece by piece, right? And we'll go through all the different notations. So first, we'll deal with this notation, right? This is saying the second partial derivative of z with respect to x 2 times, right? So this means I take the first partial derivative with respect to x and the second partial derivative with respect to x. Another notation that you could see, just so we're not surprised, right? This is the same thing as f sub xx of xy, right? Again, this is saying take the first partial with respect to x and the second partial with respect to x. We'll do this one more time, or a couple more times actually. We'll do the second partial derivative of z. Let's do with respect to y both times. Right, so again, this is saying I take the first partial with respect to y and the second partial, right, different notation, but meaning the same thing over here. And we have a couple more, but I'll write it out. Now, let's go ahead, we'll write this out. We have our second partial of z, so this part's still the same. But now, let's say I want to take the first partial with respect to x, that's a partial derivative, but I want to take the second partial with respect to y. Right, so that means I take the first partial derivative with respect to x, I take the second one with respect to y, and this is equal to, right, we can write this as f of x, y. And now what I want to mention here, I'm going to write it going across the bottom, is that if we are continuous on our domain, right, if we are continuous on our domain, it does not matter the order in which I take the partial derivative. So what I'm saying is this is equivalent to f of yx, right? It does not matter the order that I'm taking these. Right, so in other words, right, just to keep it going all the way across, right, I can flip the order here, right, the notation, and it's equivalent only if I'm continuous on the domain. First partial with respect to y now, and second one with respect to x. And we're going to test this out just to make sure. Right, so this is all of our notation. Again, the interpretation here is the concavity. So let's go ahead and do an example. We'll say z is equal to, we'll do our same one, but we'll switch it up a little bit just to make it semi-interesting. 2x squared plus 3y squared plus 2yx. Okay, so we'll do our first one. I'm just going to simplify it by writing f of xx, or you could write z sub xx. Right, so we'll write z sub xx, or we'll do z sub x first. Right, we have 4x, a derivative of 3y squared with respect to x goes to 0, and we end up with 2y. Okay, we take the second derivative, z sub xx, meaning we're just going to take the derivative again. Well, derivative of 4x with respect to x is 4, and derivative of 2y is 0. Right, so z sub xx here is 4. So again, first partial with respect to x, second one with respect to x. Let's go ahead and go for the y's. We will do, let's do it in blue. So we'll say z sub y is going to be equal to, well, this is going to be 0, right? That's just a constant. This is going to be 6y plus 2x. If I take the second partial, z sub yy, what happens? Partial with respect to y, I get 6, and 0 over here, right? So just 6. In this case, our second partial derivatives are 4 and 6. Now, I want us to also remember, this is a little bit skipping ahead, but remember what the interpretation is of positive concavity, or positive second derivatives, and negative second derivatives. We'll get to that in the next video, but pay attention to that as we do this. And finally, right, we're going to go for both the second partials. Now, I've already done some of the work, right? So we'll say z sub xy is equal to, right, so I look at my z sub x and I'm taking the derivative with respect to y, I get just 2. And I can do the same thing here for z sub y. Right, what do we notice? I'll put a comma here, just so we can prove a point. So z sub yx, well, if I look at z sub y and I take the partial derivative with respect to x, I also get 2. So again, these two will be equivalent if we are continuous on our domain, which we are here, right? Meaning I can plug in any x and y. Okay, so again, go through the notation, get comfortable with the notation. I know it's new. Again, the interpretation here is the concavity in each particular direction, right? So the concavity in the x direction is positive 4, meaning it's always going to be what? Concave up. Same thing here, positive 6, always concave up. We don't need to know that so much yet, just really on how to calculate the second partial derivatives. Okay, and the next part of the video, we'll go through some more examples, right? A little bit more difficult than this one, and I will see you there. Welcome back in. Now that we have an intuition on what these second partial derivatives are, let's actually get through solving them. But before we do so, right, to get to second partial derivatives, we have to go through some more practice of first partials. So let's go through this. F sub x means we're treating both y and z as the constants, right? So this is going to be 2x, y and z are constants, y to the 9th, z to the 8th. Over here, derivative of x is just 1, so we're left with 8 y squared z cubed. Awesome. Moving on to f sub y, we're treating x and z as the constants. Switch color markers here. So derivative of y to the 9th, we have a power rule. The 9 comes down in front. X squared is a constant. Finish off the power rule. Z to the 8th. Plus derivative of y squared. 2 comes down in front. 16 y squared, or just y, x, z cubed. Right, so just a lot of power rules here. And finally, f sub z, we're treating both x and y as constants. We end up with 8, right, from z to the 8th, x squared, y to the 9th. We'll finish off the power rule, z to the 7th, plus, over here, treating x and y as constants, the 3 comes down, 24. We have x squared, or y squared, x, z squared, right? Awesome. Right, so now we have all of our first partial derivatives. We can go work on some of the second partial derivatives. Obviously, I haven't written them all out. There would be a bunch here since we have x, y, and z. But we'll do a couple just so you get the feeling. So f sub x, y, right? What this is saying is our first partial derivative is with respect to x, which we've already done right above. Right, so in our second partial is with respect to y. So we're going to take our first partial derivative with respect to x, and now take the derivative again with respect to y. And let's see what happens. So we have the 9 come down. The x stays in place. We have y to the 8th, z to the 8th, plus, what's the next one? Again, with respect to y, we have 16 y z cubed. Awesome. Okay, so again, first partial with respect to x, second one with respect to y, and now we're going to do the opposite. So first partial with respect to y, second partial with respect to x. So we already have our first partial with respect to y. We're now going to do the derivative again with respect to x. So derivative of 9x squared y to the 8th, z to the 8th with respect to x. 18x y to the 8th, z to the 8th. And now derivative over here with respect to x, right, plus 16 y z cubed. Awesome. Now what do we notice before we move on to our next one is that these are equivalent, right? So if a function is continuous on the domain, it does not matter in which order we take the partial derivatives. Here in this case, fxy is equivalent to f sub yx, right? It doesn't matter which way you take the partial derivatives. Obviously, there's a lot more second partial derivatives we can do. I'll hold off, I'll let you do those as good practice, and we'll move on to our next example. So back to this, we have to go through our first partials first to get to our second partials. We're going to take the partial derivative of our function v with respect to s, right? In this case, we have a chain rule. So derivative of the outside function is cosine of negative 2s squared plus 4t squared. And derivative of the inside with respect to s. Right, well, what is that? That is just negative 4s, right? Awesome. And one more time. So now the derivative of the outside function is going to be the same, right? Because this is composed of both s's and t's. So derivative of sine is going to be cosine of the same thing, right? Negative 2s squared plus 4t squared. And derivative of the inside, right? This is going to be 0, and this will be 8t. I gave myself a little bit too much room, but that's okay. So now we have our first partial derivatives, right? Both of them use the chain rule. Unfortunately, now let's read this bottom one, right? So it says the second partial derivative of v with respect to s squared. What does s squared mean? It means that my first partial was with respect to s, and my second partial will also be with respect to s. So I need to do it one more time with respect to s, but that means we have what? A product rule. So let's walk through it. So our first, right, product rule, we take the derivative of the first, so derivative of negative 4s with respect to s, negative 4. We're going to leave our second function alone, negative 2s squared plus 4t squared. And now we're going to do the opposite order, right? So now we'll leave our first function alone, which is negative 4s. And we're going to take the derivative of cosine, right? Well, so cosine of this, right, the inside function, we have another chain rule. So derivative of cosine is going to be a negative sign, right? So this will switch over to a positive. So we have sine here. We leave the inside alone for right now. Negative 2s squared plus 4t squared. And we take the derivative of the inside again with respect to s, which is going to be another negative 4s. Right, so we'll write that here. Now, I don't have any room to simplify this algebraically, right, but it might be smart to combine the 4s, the negative 4s, to get a minus 16s squared, and write this so it looks a little bit more fluid. Right, so again, I know I skipped some partial derivatives. I just want to get a good practice on first partial derivatives. And if we know how to do first partials, we're just repeating the process for second partial derivatives. Again, we want to remember the interpretation of concavity here. So that is it for this video. Hopefully this helped for partial derivatives. I will see you in the next one.